Hello, welcome back to Discrete Math. This is lecture 8. Today we're going to talk about proofs and do a little bit of an introduction to different proof methods. So the first one that we're going to talk about is called the direct proof. And the goal here is to show that a conditional statement, if P then Q, is true by simply showing that, well, if P is true, if that's one of our starting premises, we can arrive at the conclusion that Q must also be true. Okay, so let's take a look at this first example here. It says, show that if n is an odd integer, n squared is also an odd integer. Okay, so this is our p, this is our antecedent, and the second part is going to be the q, that's going to be our consequent. So we want to show that that p implies q. We can conclude q from p. So let's start off by assuming that we have some odd integer n. Now, when we do these sorts of proofs, we can represent an odd integer in this sort of fashion, 2k plus 1 for some integer k. And if we were dealing with even integers, we would represent that as n is equal to 2 times k. Once we multiply 2 by any integer, it's going to become even. Once we shift that even integer by 1, plus 1, or minus 1, we're going to get an odd integer. Okay, so this is starting with n is an odd integer. So that is equal to 2k plus 1. And then we're making a claim about n squared being an odd integer. So let's go ahead and just do some arithmetic and algebraic steps on this to see what we get for n squared. And can we represent n squared in a similar fashion and show that it is indeed odd? So if n is equal to 2k plus 1, n squared is going to be equal to 2k plus 1 squared. We expand that right-hand side. We'll get 4k squared plus 4k plus 1. Now, as it stands, it doesn't look like it's really in this format of 2 times something plus 1. But let's see if we can rewrite it as such. So I've got a 4 in the first two terms. I can factor out a 2 from each of those terms. So I'll have 2 times, in parentheses, 2k squared plus 2k, all of that plus 1. And just by getting here to this point, I've got this into the form of 2 times something plus 1, even if that something is, some other operation or expression. That's fine, as long as this is an integer, this holds. And this will be an integer because we've only ever been working with integers. So if you wanted, you could represent that parentheses as some other letter r, some other integer r, which means n squared can be represented as 2 times r plus 1. And therefore, n squared is also odd. All right, so that's what we have. N squared is also an odd integer. So that's direct proof. We start with our P as an assumption, and we show that it leads to Q as a conclusion. So this is probably the most straightforward way of establishing or constructing a conditional statement. But we've got another technique that will work for this, and this is proof by contraposition. Okay, so this is making use of this equivalence that we talked about before. So if P then Q is equivalent to its contraposition, which is the conditional statement, negation Q implies negation P. Now, in some cases, it might be really difficult to start with P, whatever that antecedent is. And it'll be a lot easier to work instead with the negations of these things, right? But you can establish that same relationship, if P then Q, by first establishing this relationship. If negation Q, then negation P. Okay, so we can prove that conditional statement by showing that its contraposition is true. And this is a really powerful tool. So let's look at this example. Prove that if 3n plus 2 is odd, then n is also odd. Okay, so 3n plus 2 being odd, we're going to call that our p. That's the antecedent of this conditional that we're trying to construct. N being odd, we're going to call that q. That's our consequent. Okay, now we're going to start. Now, instead of by assuming that p is true, we're going to start by assuming that negation q is true. So if q means n is odd, then negation q is going to be the opposite of that. N is not odd or n is even. Okay, so because we're only dealing with integers, if it's not an odd integer, it has to be an even integer. Okay. Now, just like we were saying before, if it is an even integer, we can represent it in this fashion: 2 times k for some integer k, because whatever integer you have out there, if you multiply it by 2, it will become even. Now, we're starting with n, but we want to prove something about 3n plus 2, right? This is sort of starting with the idea that if n is even, that's what our negation q means, then negation p is going to mean then 3n plus 2 is also even, right? Because that would be the negation of p. If it's not odd, then it's even. So let's show that this is the case. So we're going to substitute in this 2k here for n in the 3n plus 2. So we're going to get 3 times 2k plus 2. If we simplify that right-hand side, we're going to get 6k plus 2. Now, our goal is to show negation p, which means 3n plus 2 is even. So much just like the last sort of problem, we're trying to get into this form. Last time we were trying to get into the form of 2 times something plus 1 for an odd integer. This time we're just going to try to get this into the format of 2 times something. So can we represent this as 2 times something? Indeed we can. We can factor out a 2. And we'll just have 3k plus 1 in parentheses. Because k is an integer, these operations of just multiplying by 3 and adding 1 keep it as an integer. We haven't done anything to change that fact. So we can represent 3k plus 1 as some other integer r, and therefore we have shown that 3n plus 2 is really just equal to 2r, and therefore it is even. Okay. So what we did is that, we're starting with if 3n plus 2 is odd, then n is odd, but what we actually showed is that if n is even, then 3n plus 2 is even, and this is if negation q, then negation p. Okay, and this is the contraposition. And therefore, by that contraposition, by that equivalence, if this statement is true, we can conclude that this statement is true. Therefore, if negation q implies negation p, p implies q. So that's interesting. So we were making a claim. We actually proved something about odd integers when the entire time we just worked with even integers. Okay, so that's the kind of the value of proof by contraposition. Sometimes, in this case, it's equally simple to work with even and odd integers, but we might be dealing with something like rational versus irrational numbers or something like that, where irrational numbers might be very difficult to represent in some sort of general fashion, but rational numbers, as we're going to see a little bit later, are pretty straightforward to represent. So sometimes it's a lot easier to just work with the negation of something than that thing itself. And proof by contraposition allows us to go ahead and make a claim about, say, irrational numbers while working entirely with rational numbers, or odd numbers when we're working entirely with even numbers, and so on and so forth. So this is a really useful type of proof method. Okay, so our next big technique is called proof by contradiction. Okay. So the way this works, to prove a statement P to be true, we can show that assuming its negation, assuming the opposite of P, will lead to a contradiction. which can be represented in the general format R and not R, right? Something like if we go back, it is daytime and it's not daytime in the same place, right? That's a contradiction. So if we can show that, well, the opposite of P leads to some sort of nonsensical conclusion, it must be the fact that P is true. Okay? So we're showing that its negation implies a contradiction. So let's suppose we want to prove that the square root of 2 is irrational. Okay? And we're going to do this by showing that the square root of 2 cannot be expressed as a ratio of two integers. And this is kind of going back to the idea that we were just talking about with contraposition. Sometimes it's very difficult, right? It's very difficult to represent something as an irrational number, but we can represent it as a rational number. We can work with its opposite, and we can show in this case that that's going to lead to a problem. That's going to lead to a contradiction. So let's see what happens. So we're going to start off with assuming the opposite. Square root of 2 is a rational number. Okay. So a rational number, we can represent that as a ratio of two numbers, a and b. It's just a fraction. Okay, so for some integers a and b, which are in lowest terms, and this part is really important. So we have to be able to put any rational number in some more simplified fashion. And we're going to define a and b as that, or that ratio of a and b as that simplest form. They have no common factors. We should not be able to cancel out anything from these two. Okay, so it's no different than saying we're assuming something like 2 over 3. They have no common factors. We should not be able to simplify any further than this. All right. So let's go ahead. We'll square both sides. So if the square root of 2 is equal to a over b, then 2 is going to be equal to a squared over b squared. So far, so good. Let's multiply that b squared over to both sides, right? So we'll have 2b squared is equal to a squared. Now from here, right, this idea of the even and odd, it keeps coming back, right? If you can represent something as 2 times an integer, you've shown that it's an even integer. And we've done that here, right? So a and b are integers, therefore a squared and b squared are integers. And if we multiply b squared by 2, that results in an even integer. Therefore, a squared is even. And if a squared is even, a must also be even. Now, in the first proof, we show that this holds for odd integers. You can easily just show this same relationship holds for even integers, right? So we're just kind of taking this rule a little bit on faith here, but you can absolutely easily show this by direct proof or proof by contraposition, however you like. Okay, so if a squared is even, a must be even. Okay, so far so good. That's fine. We can still have a fraction in lowest terms if the numerator is even. There's nothing wrong with that, right? Now let's see what happens with the denominator. Okay, well, if a is even, then we should absolutely be allowed to represent this as 2 times k, just some generic even value. K is just some integer. We haven't used that here in this case yet, so there's nothing wrong with just saying, well, a is just some even integer. What does this imply about b? Well, if we go ahead, we square this whole thing out. 2b squared is going to be equal to 4k squared. And that implies that if I divide both sides by 2, b squared is going to be equal to 2k squared. All right, well, this is starting to look a lot like step 4. A squared was 2 times an integer squared, and we concluded it was even. We can actually make the same conclusion now about b. b is 2 times some integer. Sorry, b squared is 2 times some integer. Therefore, b squared is even. And by the same line of reasoning, if b squared is even, b is also even. This is going to lead to a problem. If both a and b are even, we're not dealing with a fraction like 2 over 3. Now we're dealing with a fraction like 2 over 4. And that's not going to be in lowest terms. If you have a ratio of two even integers, it's not in lowest terms because we can always cancel out a 2, right? That 2 is a defining feature of an even integer. So this is contradicting that assumption that we initially made that A and B are in lowest terms and they had no common factors. Okay? Therefore, this assumption led us to a contradiction. And therefore, that assumption must be false and its opposite must be true. The square root of 2 cannot be represented in this fashion. It cannot be represented as a ratio of A and B in lowest terms. Therefore, it is an irrational number. Okay, so this is the power of proof by contradiction. So while it's very difficult to start off with an assumption that something is an irrational number and represent it in some sort of generic way, it's a lot easier to work with this representation of it as a rational number and then show that that leads to things going wrong completely. Right? So that is proof by contradiction in action. Our next big proof method or strategy is called proof of equivalence. Now, the idea here is that we're trying to show that two statements P and Q are equivalent by showing that the implication holds in both directions. So P implies Q and Q implies P. Okay? So this is kind of going back to your biconditional that we had in the beginning with propositional logic, right? So they're essentially equivalent statements if one implies the other and the other implies the first one, right? Now you can do this, right? You can establish these conditional relationships using whatever methods you like. You could use direct proof, proof by contraposition, proof by contradiction. It doesn't matter how we do it. We don't even have to use the same method for each direction. If it's not simple that way. Okay. So let's suppose we want to prove that relationship about evens. That's that same claim that we had used before, that property that we used before, that if n is even, n squared is even, and if n squared is even, then n is even. Right? We want to show that these are equivalent statements, essentially. So we're going to start off, we're going to show that this, first of all, holds in this direction, in the P, if P then Q direction. So if n is even, then n squared is also even. Okay, so we'll try to just do this by direct proof. Let's assume n is even then. And that means n is going to be equal to 2k for some integer k. We go ahead, we square that. N squared is going to be equal to, in parentheses, 2k squared. That expands to 4k squared. You can factor out a 2, right? To show something is even, we just need to show it's 2 times something. Some integer, right? And 2k squared is, of course, going to be an integer as long as k is an integer. You can replace that 2k squared with r. So we've shown that if n is even, n squared is also even. It's just equal to 2r. Okay, so we've established this first direction by direct proof. Okay, so this is no different than that first example we were using. We did direct proof to show that if, here we are, if n is an odd integer, n squared is also an odd integer. So we just did the same thing here, showing that if n is an even integer, then n squared is also an even integer. Okay? Now we want to show this the other way as well. Show that Q implies P. If n squared is even, then n is also even. And we can do this by direct proof. We can also do this by using proof by contradiction. We can show that the negation of this conditional leads to some sort of contradiction. Okay, so this may not be the simplest way to do this in this case, but I just want to show you that we don't have to use the same methods. We can use any of these methods to establish this. Okay, so this is going to require. So if we're going to do the negation of a conditional, we have this alternative definition of a conditional, right? This is that conditional disjunction equivalence. So you can represent that conditional if Q then P as the disjunction negation Q or P. So if we substitute that in inside the parentheses, and then we use De Morgan's law, negation of a negation is that original statement. That disjunction turns into a conjunction, and this negation goes onto that P. It's almost like we're distributing that negation. And that means we have to flip the sign, or flip that conditional, that conjunction into a disjunction, or disjunction into a conjunction. All right, well then, we're starting with this assumption then. Q means n squared is even. So we're gonna assume n squared is even. That's what Q means, right? And that's what we have in our final, so we've rewritten this as this conjunction. Okay? Now, for the sake of contradiction, we want to assume that n is odd. Okay? P means n is even. But when we're negating this, when we're doing this proof by contradiction, we negated that initial premise, and we arrived at n squared is even, and n is odd. That's what negation P means here. Okay. So all we're doing is we're just assuming each parts of this conjunction. Okay, well, if n are odd, then we can represent n as 2k plus 1. And if n is equal to 2k plus 1, then n squared, we're going to go ahead and we're going to square that thing. We can expand this. 4k squared plus 4k plus 1. We can factor out, just like we did in the very beginning, we can factor out 2. And this also becomes 2 times something plus 1. That's something, we can just call it r. Therefore, n squared is equal to 2r plus 1. And n squared is also odd. Except we started by assuming that n squared was even, right? So we assumed that n squared was even and n was odd simultaneously. And what this does is this leads to a contradiction. These two statements cannot be simultaneously true. Okay, so this contradicts with line 1. Okay, therefore, by contradiction, we've proven that this cannot hold and its opposite must be true. So the negation of Q implies P is not true, therefore Q implies P. Okay, so we've shown that this is going to hold in both directions. We've established if P then Q by direct proof, if Q then P by proof by contradiction. Therefore, these statements are equivalent. And that completes our proof of equivalency. Okay, and again, you don't have to use proof by contradiction if you feel like that's a more complicated method for trying to establish whatever you're trying to do. You could have just used direct proof or proof by contraposition. They would have also worked just fine. But the idea here is to demonstrate that we don't have to be limited necessarily to one method of proof. All right, let's look at the next example and see if we can identify what's wrong with this. What's wrong with this proof? All right, we've got a lot going on here. Okay. We start with this statement. A is equal to B. That's our premise. Then we multiply both sides by A. Okay, that's fine. That's mathematically legal. We're multiplying, we're doing the same operation on both sides of this equation. It's perfectly acceptable. We get A squared on the left side is equal to A times B on the right side. And then they say, well, can we subtract B squared from both sides? And that seems perfectly mathematically legal as well, right? We're doing the same operation to both sides. All right, well, a squared minus b squared, that's the difference of squares. That factors to a plus b times a minus b. And on the right side, they just took out a b from both of these. So we're going to get b times a minus b. So now we've got the same factor, a minus b, appearing on both sides. They divide by that. And now we'll be left with a plus b is equal to b. Well, in line 1, a was equal to b. So we can replace that a with b. So we're going to get b plus b is equal to b, which simplifies to 2b is equal to b. Okay, interesting. And then they said, well, let's just divide both sides by b. And therefore, 2 is equal to 1. Huh. Well, that's not true. It's just clearly something here went wrong. All right. So take a moment to figure out, see if you can figure out what went wrong here. What step wasn't legal or correctly applied here? What mistaken assumption was made? All right. Well, hopefully you've taken some time to think about it. Now, let's remember that we started with this assumption that A and B are the same value. We didn't specify what values they were. We can assume that they're just some sort of integers. It could be real numbers, rational numbers. They could be irrational numbers. But if they're the same number, then that means if we were to subtract the two of them, we should be getting 0. A minus B has to be 0. But if you look on step 5, from step 5 to step 6, we went ahead and we divided by A minus B, right? In other words, we divided by 0, which is not a legal operation. Division by 0 is undefined in mathematics, and rightly so, because it can lead to absurd conclusions like this, right? Where a plus a number plus itself will equal itself. And you can get that all the way down to 2 is equal to 1. Now, you might say, well, this sort of thing might hold if a and b were both 0, right? 0 is equal to itself. But in that case, we still can't divide by a minus b because we're still dividing by 0. Okay, and if it were the case that there was 0, then we would have, again, made the same exact error in line 8. Okay, so we should not have been dividing these at all. And that is, in fact, what led to this mistake here. All right. So that's just a quick example of how to look out for mistakes in proofs that might seem perfectly legally valid, but we have to think about what's happening behind those variables. What do they imply? What does this mean numerically or otherwise, right? So it's a good example of something to look out for. Now we've got another method of proofs. This is called proof by cases. Okay. So this type of proof has to address all possible cases that might arise in a theorem. Okay, so until now we're just kind of talking about even and odd integers, and if we make a claim about one even integer, some arbitrary n is equal to 2k, well, this kind of holds for all other even integers. And the same with if we make an arbitrary odd integer, we make some claim about this or this squared, this is going to hold for all of those odd integers. But what about cases where we think about maybe both even and odd at the same time, or both positive and negative at the same time? Okay, so let's see an example. So this example says, prove if n is an integer, n squared is greater than or equal to n. All right, well, if n is an integer, we have to think about the 3 following cases, which cover all integers. So case 1 is that n is less than or equal to -1, meaning it is a negative integer. The second case, well, n is equal to 0. That's also an integer. In case 3 is, of course, n is greater than or equal to 1. N could be a positive integer. So we have to show that this holds for each of these three cases. Otherwise, we're not covering all integers. We're either covering 0, we're covering positives, we're covering negatives, right? So we need to show that it holds for all of them. So that's fine. We'll investigate this case by case. So we start with case 1. N is less than or equal to negative 1. So when n is less than or equal to negative 1, n squared, well, any negative integer squared is going to be positive, right? Negative times negative is positive. Well, then this fact, or this theorem holds. N squared is greater than or equal to n, because any positive number is greater than or equal to any negative integer, right? All right, well, case 2. So we've shown that works for case 1. Case 2, what happens when n is equal to 0? When n is equal to 0, n squared is also equal to 0. And this holds again. N squared, we said it has to be greater than or equal to. In this case, they're equal. N is equal to n squared when n is equal to 0. That meets this criteria, so that works. So it holds for case 2. And finally, we just need to show that it holds for positives. Well, when n is greater than or equal to 1, we can actually just take this and just go ahead and multiply both sides by n. And that will lead us directly to n squared is greater than or equal to n. Okay, so that just sort of falls right out of the definition of a positive integer for that positive case. Okay? Therefore, this theorem, this idea holds for all three cases. Okay, so this law holds for all three cases. That's just a quick example of how proof by cases works. Okay. And the last method that we're going to talk about is called proof by backward reasoning. Okay, so until now, we've been kind of moving forward. We start with our initial premise, say P, we show that this leads to Q, and we've got this implication, P implies Q. Okay, so until now, we've been doing what's called forward reasoning, direct proof, proof by contrapositive, and so on. We start with the axioms and known theorems, and we construct a sequence of steps that ends in that conclusion P, right? But if this doesn't work, we can do what's called backward reasoning. So when we're trying to prove Q, we can look for some statement P that we can prove with the property if P, then Q. So let's see what this looks like. Okay, so we're going to work backwards. So let's suppose we've been given two positive real numbers, x and y. Their arithmetic mean is just going to be x plus y divided by 2. That's just your typical average. Their geometric mean is defined as the square root of x times y. Okay. So when we compare these means for pairs of distinct positive integers, positive real numbers, so distinct meaning x is not equal to y, we find that the arithmetic mean is always greater than the geometric mean. Okay. Can we prove that this inequality is always true? Okay, so we've observed that this tends to always be the case. Is it really always the case, right? This is going to always work in general. Right, so our goal is to prove that if x and y are distinct positive integers, then this inequality holds. X plus y over 2, the arithmetic mean, is greater than the square root of x times y, the geometric mean. So let's work backwards by constructing a series of equivalent inequalities. So let's start with the thing that we're trying to prove here. Right, x plus y over 2 is greater than the square root of x times y. We can square both sides. Right, so get this x and y out of the radical here on the right side. So we're going to get x plus y squared on the left side over 4 is greater than x times y. Our next step, we can multiply this 4 over to the right. X plus y squared is greater than 4xy. Okay, so we haven't done anything special. We're just doing arithmetic and algebraic operations on that same inequality. We're going to see where this leads us to. Okay, ideally, we want to show somehow that x and y are distinct positive integers. All right. Next, we expand this square. We can FOIL this out. We're going to get x squared plus 2xy plus y squared is greater than 4xy. So all we're doing is we're expanding that left side. Let's bring over this 4xy to the left side. We'll subtract 4xy from both sides. That'll leave us with 2xy minus 4xy. It's going to be negative 2xy. Now this kind of looks like this old definition, a squared minus 2ab plus b squared, which is equal to a minus b squared. So we can factor this left side back into this format. And we're going to get that x minus y squared is greater than 0 by applying this property. Now, x minus y squared being greater than 0, what does that mean? This can only be true if x is not equal to y, right? If they were the same thing, their difference would be 0, and squaring their difference would still be 0. But if it's greater than 0, if it's some value other than 0, then that means these numbers are not the same, okay? So this inequality that we started with follows directly from this. Well, they follow from each other, right? So one leads to another. They're just by writing a set of equivalent inequalities, we can get from one to the other. All right, so because all of these inequalities are equivalent, it follows that if x is not equal to y, they are distinct values, then the arithmetic mean is indeed greater than the geometric mean. All right, so that is what a proof by backward reasoning looks like. All right, so this was a little bit of an introduction to some proof methods. This was lecture 8. I hope you found this video helpful. If you did, please make sure to like the video and subscribe to the channel for more content.